The ocean's true apex predator may have finally been exposed. In November 2003, off the southwestern coast of Australia, a research team clipped a small data logging tag onto the dorsal fin of a healthy 9-foot great white shark. She was calm, confident, and completely unbothered by the boat alongside her, the kind of animal that had never once had a reason to think of herself as prey. The crew started calling her Alpha. For months later, her tag washed up on a beach more than 2 miles from where it had been attached. The shark herself was never seen again. When researchers finally read the data stored inside that tag, they found something that didn't match anything in the existing science of the world's most feared predator, and the explanation it pointed toward took years and a fair amount of professional discomfort to say out loud. An animal with nothing to fear. To understand why Alpha's disappearance mattered, it helps to understand exactly what she was. Great white sharks sit at the top of the ocean's food chain for good reason. Fully grown adults can exceed 20 feet and weigh well over a ton, armed with rows of serrated teeth that continuously replace themselves and sensory organs capable of detecting a single drop of blood in an enormous volume of water, along with the faint electrical signature of a heartbeat hidden under sand. In short bursts, they can close distance on prey faster than that prey can typically react. At 9 feet and roughly 500 pounds, Alpha wasn't a juvenile still learning the boundaries of her world. She was a fully mature adult, an animal that had spent her entire life without a natural predator of her own. The tag placed on her wasn't a live tracker, beaming her position back to a lab in real time. It was an archival tag, a self-contained device built to quietly record depth, water temperature, and light levels for months at a stretch, storing everything internally until a preset release date, at which point it would detach, float to the surface, and transmit its data via satellite. That meant nobody was watching Alpha directly once she swam off. Whatever happened to her out in open water happened without a single human witness, filmed by nothing but the small archive of numbers ticking away inside a device clipped to her fin. The numbers that didn't add up. When the tag was eventually found and its data extracted, filmmaker David Riggs, who had been documenting the tagging project, and the research team behind it expected exactly what most shark tracking data shows: gradual movement patterns, slow shifts in depth, and temperatures cooling predictably the deeper she went. That isn't what the tag recorded. For months after deployment, the data showed an abrupt, rapid descent to a depth of roughly 1,903 feet, more than a third of a mile straight down, occurring within a matter of minutes, rather than the gradual dive pattern typical of the species. Great white sharks are not built as deep ocean specialists. The overwhelming majority of their lives are spent within the sunlit upper layers of the water column, close to the coast, close to abundant prey. A sudden plunge to nearly 1,900 feet, executed quickly and without any gradual buildup, was already an outlier for the species on its own. But depth alone wasn't the detail that stopped the research team cold. It was what happened to the temperature reading at the bottom of that dive. At 1,900 feet off the Australian coast, ambient water temperature sits around 46 degrees Fahrenheit, cold enough that it should only get colder the deeper the tag descended. Instead, the recorded temperature spiked sharply upward, climbing to a sustained 78 degrees Fahrenheit, a jump of more than 30 degrees in exactly the wrong direction for that depth, and it didn't fluctuate or fall back the way a malfunctioning sensor might. It held steady. There's really only one plausible explanation for a tag logging a stable, warm 78 degrees in near-freezing deep water. It was no longer in the ocean. It was inside something, some living animal with a warm internal cavity that had swallowed shark, tag, and all, then carried the meal down into deep water to finish it, working through the suspects. Faced with that combination, roughly 1,900 feet of sudden depth paired with a warm, stable internal temperature, the research team worked through the realistic candidates capable of consuming a 9-foot shark whole and eliminated them one at a time. Orcas were an obvious early candidate, since they're documented predators of great whites in places like South Africa, using a precise technique to flip sharks into a paralyzed state before extracting a liver. But orcas are not deep divers in any sustained sense. and their recorded dive depths fall well short of 1,900 feet. The behavior didn't fit the body. Sperm whales, by contrast, are genuine deep divers capable of reaching far greater depths than Alpha's tag recorded, and a throat that size could easily accommodate a sharker size. But sperm whales run internal body temperatures around 97 to 99 degrees Fahrenheit, far warmer than the 78-degree reading, and their diet is built around soft-bodied deep-sea squid, not large muscular predators. Wrong temperature, wrong prey profile. Other large sharks, such as tiger sharks or oceanic whitetips, were considered and ruled out on simple math. The largest recorded tiger sharks top out around 14 feet, and swallowing a 9-foot shark whole requires a predator dramatically larger than its prey, not merely somewhat bigger. A colossal squid was floated briefly as a theoretical possibility capable of dragging prey into deep water. But squid are cold-blooded invertebrates with no internally warmed body cavity at all, which ruled that idea out on the temperature evidence alone. An uncomfortable answer. Every deep-diving candidate ran too warm-blooded and wrong diet, and every candidate with a plausible temperature profile couldn't reach the depth. That left the research team somewhat reluctantly, according to later accounts, with a conclusion that seemed almost too straightforward. Another great white shark, considerably larger than Alpha, was very likely responsible. Great whites belong to a small group of sharks with an adaptation called regional endothermy, meaning they can retain metabolic heat generated by their swimming muscles well above the surrounding water temperature, keeping their core organs and digestive system meaningfully warmer than the ocean around them. A typical adult great white stomach might run somewhere in the range of 65 to 70 degrees Fahrenheit. A significantly larger individual with substantially more muscle mass generating and retaining heat could plausibly produce and sustain something closer to that 78-degree reading. And while great whites are usually associated with shallower coastal water, tracking studies have recorded them diving well past 3,000 feet in open ocean settings, meaning a dive to 1,900 feet, while extreme, isn't outside the species' documented capability for a sufficiently large individual. Using a rough rule researchers apply to this kind of predation, that a predator typically needs to be roughly twice the length of prey it swallows whole. A shark capable of consuming a 9-foot great white would need to be somewhere in the neighborhood of 16 feet long and well over 2 tons, sitting at or beyond the upper documented range for the species. How confident should we actually be? It's worth being honest about where this conclusion sits scientifically. The predation interpretation of Alpha's data comes primarily from the research team and David Riggs, and was popularized through a Smithsonian Channel documentary, Examining the Case. It's a well-reasoned inference built from real recorded data, but it is an inference rather than a directly observed or independently confirmed event, since no camera, diver, or second tag ever captured the moment itself. Some scientists and science writers have pushed back on how definitively the case has been presented in popular media, noting that while the temperature and depth data are real and genuinely puzzling, labeling the culprit with total certainty goes further than the data alone can prove. The honest scientific position is that a large great white remains the best supported explanation among the options considered, not an established fact beyond dispute. Cannibalism isn't as rare as it sounds. What makes the great white explanation more plausible than it might initially seem is that predation among great whites on their own kind isn't some unprecedented anomaly. It's a documented, if still poorly understood, part of the species' behavior. Larger individuals are known to dominate and displace smaller sharks at shared feeding sites. Juveniles face genuine risk from larger adults sharing their range. The behavior even appears to begin before birth, since developing great white embryos are known to consume unhatched siblings in the womb, a phenomenon well established in the scientific literature. Carcasses of great whites have washed ashore bearing bite wounds, whose spacing and serration pattern are consistent only with the jaws of another great white, and researchers and divers have photographed living sharks carrying old, healed scars matching that same signature, evidence of an attack survived rather than one that proved fatal. Taken individually, each of these cases could be written off as isolated aggression, a territorial dispute over a carcass rather than deliberate predation. Considered together, alongside the specific depth and temperature signature recorded on Alpha's tag, They support a more unsettling pattern. The largest great whites don't just compete with smaller members of their own species. On occasion, they eat them. A ceiling that isn't fixed. If that's accurate, it complicates a long-standing assumption in marine biology, the idea of the great white as a fixed, singular apex, a ceiling above which nothing else in the ocean operates. The evidence instead suggests the apex position within the species itself is relative to size, with the largest, oldest individuals occupying a tier that smaller sharks, even fully mature adults, like alpha, don't reach. And there's a structural reason we might be missing exactly these animals. Research tagging efforts disproportionately capture younger, smaller sharks that stay closer to coastlines where boats and researchers operate, while the largest, oldest females are believed to spend much of their lives far out in deep, open water, well outside the range most tracking studies cover. It's a sampling bias built into how this research gets done, and it means our picture of what a maximally large great white actually looks like may be systematically incomplete. For reference, the largest great white ever reliably filmed and measured is a shark known as deep blue, an adult female estimated at close to 20 feet long and around 4,500 pounds, photographed off Guadalupe Island, Mexico, and believed to be several decades old. There's no evidence connecting deep blue to alpha's disappearance in any way, and no serious source has ever claimed otherwise. She's worth mentioning only because she demonstrates, with direct photographic confirmation, that great whites genuinely do reach sizes at the upper edge of what the alpha case implies, which lends real-world plausibility to an explanation that might otherwise sound far-fetched. What the tag actually proved. Whatever exactly happened to alpha in the final minutes recorded on that tag, the case is a useful reminder of how much of the ocean, even involving one of its most intensively studied predators, remains genuinely unmapped. Great whites have been filmed, tagged, and studied for decades, and researchers are still uncovering behaviors, size ranges, and depth capabilities that don't match the textbook picture. A small archival tag, recording nothing but depth and temperature over 4 unwitnessed months, ended up rewriting part of that picture almost by accident, simply by refusing to describe an ordinary day in the ocean when the data plainly showed something extraordinary instead.